let me first share my screen here. All right, so Paul is not here today. He's flying, he's on his way to Hawaii, he mentioned. So it's an honor to replace Paul now and introduce John's talk today. And as Paul said, it's daylight saving time in the US already, but not yet in Europe. So that's why it's now 2 p.m. That we're hosting John. So everyone, thank you very much for being here, for attending today's Source to Sync webinar. It's co-sponsored generously by NSF and co-hosted, primarily hosted by Paul at NC State, but also LSU, SKLEC in Shanghai, Systems in Boulder, Colorado, and myself here at Utrecht. Before I introduce John, just so you know, it's an ever-expanding resource of now 105 talks on YouTube, and there's a link here that you can find to locate these talks. It's also on Bilibili for people in China. You can follow Paul and Source to Sync talks on Twitter as well, with the handle at Source to Sync to keep up with the latest updates and latest talks. So for those of you who are interested, next week, March 25th, we'll have Catherine Russell from the University of Leicester and Louisiana State University talk to us about Anthropocene rivers. And that's going to be another week where the talk will be at 2 p.m. Europe time. So stay tuned for our talk next week as well. All right, so for this week, I'm very glad John has been willing to talk to us. John is an associate professor at the University of Arkansas. Before that, he got his degrees in math and geology from Oberlin College. He then moved to Texas for his PhD, thinking about distributary channels and wax lake deltas. You probably know from John's work, of course, as well, and hope he's going to discuss that a little bit in his talk, because it's really fascinating by all things wax lake. After his PhD, he did a postdoc at the University of Wyoming, and after that, he started his tenure track at the University of Arkansas. As you probably know, John currently is not in Arkansas, but in Poland on a Fulbright fellowships, working with people at the University of Warsaw on theoretical physics. John has generally done a lot thinking about morphodynamics of delta landscapes. And as I mentioned before, very inspiring in how he's trying to link theoretical physics and math to coastal morphodynamics. And with that, John, I'll stop sharing my screen. Please take it from here.
Well, okay, yes, and share, and thank you. Thank you, Jaap, for the wonderful introduction. And I'm so honored to be presenting at this S2S Source to Sync forum. It's one of, I think it's the best thing that's happened as a result of the pandemic, almost bar none. What a great resource. And I've learned so much from it, and I continue to. So off we go. I came up with a more general talk title, Distributary Channel Networks Connecting Form and Function. I wanted to be quite overarching and talk about a lot of stuff, but I'm gonna drill down into, so we don't go very long, too long, to drill down into particularly bifurcating distributary channel networks like you see on the left here. First, I want to acknowledge the team that's worked on this, what I'm going to show you today. We've got Taewoo Chun, Chris Cathcart, Wentao Ke, Robert Mann, and Hongbo Ma, who've all worked with me at Arkansas at various times, and Elizabeth Chamberlain, who has been a collaborator of late as well. I'm currently a fellow, a Fulbright fellow in Poland, thinking about channel network physics here as well. And most of this work was supported by a Department of Energy grant, basic energy science, to look at distributary channel networks. I'll take less than a minute on this, but while I've really enjoyed getting to know Poland, it's been a tense time to be here. This has been, just a month ago, I don't think anybody could have pictured where we'd be today. And the influx of refugees into Poland from Ukraine has been just completely broke the scale of what I could think possible, and also the scale of the Polish response in particular has also broken the scale. It is an evolving and uncertain situation, but the fact that this country has taken in maybe 4% of its entire population as refugees and are housing them and feeding them with no long-term plans or long-term anticipation has been amazing. So this is a big building that was actually a Russian building on my way home, which has been appropriated and will be hosting Ukrainian refugees. So that's something that I won't soon forget about this year. So back to distributary channels. Why study them? We have a fantastic variety of channels in the world, and they are incredibly effective at moving sediment in a way that can build land. So here is one of my favorite illustrations of this. This is a small crevasse spike in the Bird's Foot of the Mississippi Delta. And in 1978, we had this basin, this muddy basin, that when this levee was cut, I think naturally, we had a very quick progradational phase of a distributary channel network, which filled up this system quite efficiently in about 22 years. So these are the processes that move sediment in such a way as to build land. So that's one really important reason. Second is we can see these distributary channel networks in the rock record. Here on the left is an image of the surface of Mars in the Aeolus Dorsa region with distributary branching channel networks here. And then on the right, we have a seismic image of the Songmiao Basin in northeastern China. This is a lacustrine basin. And here you can again see a motif of many branching distributary channel networks, likely overlaying, several cycles overlaying here. But if you focus here and yell at me if you can't see my mouse, but you can see here, these are branching distributary channels. Now, not all distributary channel networks are simply bifurcating. We have some channels, some networks which produce loops and quite a few loops. So I don't want to say nothing about these. We have a really wide diversity of channel networks on Earth's surface, but in order to keep this focused and to keep my points direct, I'm going to leave this to the side, although it's something that is near to my heart. So, channel networks, there's lots of scales to talk about these networks too. And at the largest scale, the most important process is avulsion. And I'm not going to talk about that. So if we take the Mississippi as an example with these beautiful figures from Bentley, we see that on the order of once every 500 or so years, we have a major avulsion of the system and a redistribution of where the main trunk of the system is going. So we have Tesh lobe building here. This was several thousand years ago. And then we have the St. Bernard lobe after that. And then the Fuchs lobe coming in here in about 2,000 years ago, 1,800 years ago. And while these avulsions are incredibly important in setting the large-scale distribution of sediment in the source-to-sink framework, the lobes and the plumbing of the lobes that forms very quickly as one of these systems progrades is a different process altogether than the avulsive process. So I'm going to talk about this, what sets the bifurcating structure of a lobe between avulsion events. And this is going to come, so here's my philosophical pitch to you of an exciting way that we can move forward, which is that we have many models of delta channels, of delta network evolution. We have channel resolving ones. We have a whole portfolio of things that we can use. And that is wonderful. And we have learned a lot about how systems work through hypothesis testing in these systems. What we have fewer of is models that focus on specific systems for long periods and try to model them directly over long periods. The two exemplars I can think of are this Dostgib paper from some time ago that modeled about 2,000 years of a tidal inlet in the Dutch Bight. And then this excellent, also from Donna Rovink's group, a few hundred years of modeling sediment the morphodynamics of the Ganges-Brahmaputra Delta by Yaki Akhtar. That's just come out. But over source-to-sink timescales, we have real data sets that are, we have field deltas where we know quite a lot about them. And it feels risky to model these things explicitly, but there's quite a payoff to it. I should also mention Jaap's work modeling the Ebro Delta. It's a great example of focusing on seeing what you can learn from a specific site. So that's something that I find very exciting and something I would encourage everybody to do. So the agenda for today. First, I'm going to show you that channel network growth can be synthesized with a simple moving boundary model using the Wax Lake Delta as a comparison. So I'm going to pitch you a model that I helped develop, which does away with a lot of complexity just to focus as precisely as you can on the channel itself. And then I'm going to show you the work by Taewoo Chun here, who is a recently completed master's student in my group, to use this model to model the 1,000-year evolution of Bayou Lafourche in coastal Louisiana. So that is the plan. Existing theory. Okay, so this goes back to the introductory textbooks that we're working on, is what happens to sediment when it gets to a channel mouth. And we have classic diagrams like this one from the Boggs textbook and Coleman and Wright and others that talk about the different ways that sediment can form at a channel mouth. And from these, we have single channel mouth models of how that sediment interacts with flow and maybe either extends the channel, as is done in this model by Canestrelli, or causes a bifurcation, which is discussed here in this classic Edmonds and Slingerland paper. And so the focus on how these deltas evolve is focused on these channel mouth models. So that's the state of, it's been the state of the science. And from my work on the Wax Lake Delta, I found ways that this is applicable and ways that which it falls short when you have a rapidly growing multi-channel delta. So this is the Wax Lake Delta in coastal Louisiana. It's about 100 square kilometers. And in this digital elevation model from 2015 and 2016, we can see that the greens up here are shallow to emergent above sea level areas, and then the reds to whites are deep areas. And rather than a channel mouth, we have a very gradual transition from channelized flow to unchannelized. So the abrupt channel mouth, which is the prerequisite for a lot of turbulent jet theory, can't be placed anywhere. The topography really matters. And the other part of this is, okay, so here we have a radar image of the system. And what you can see is down here in the red arrows, we have vectors of velocity from an ADCP that chugged along during this time. And you can see that while there are subaqueous channels, which are moving most of the flow, the entire system and all the way up through here and further is waterlogged and moving surface water across the system. So there is no dry spot on this delta. And that influences how your hydrological model should behave. Especially when a turbulent jet model is predicated on having no outflow lateral to the channel, which influences how the spreading and deposition occurs. So those are 2 episodes. And then for 30, we have surveys of a distributary channel in this system. And over time, these deep channels are extending into these shallow delta front domains via erosion. So these reds show each time, between each period, how these channels inched forward. And so this is the Wax Lake Delta. There's also some great modeling by Andrew Moody and co of the Yellow River Delta, which is one of the most sediment-laden river systems in the world. Bar none, it's a highly depositional, or it's got more load coming into the system than just about anywhere else. But even so, as this system progrades, as you can see from the darks to the lights here, you have, even though the thalweg is aggrading due to the giant sediment load, the channel tips are extending downstream by eroding. So we need to have a model that makes our distributary channels move forward by erosion. So let's build a model. And the goal here, the conceit of this model is to sell out entirely, do everything we can to track the progradation of channels and focus our the resolution of the model along the channel network boundary and track the movement of that channel network. So that's what we're going to try to do. So the first thing that we do is we take the shallow water equations for fluid flow, which work in nearly all coastal environments, and we're going to linearize them such that we're going to model flow in over a flat, unchannelized domain with the Laplace equation here. So this is a simplicity for a few reasons. First is that it's been shown to accrue very little error in regions where we have little changes in topography and large length scales. It also it's somewhat inexpensive relative to more complex nonlinear models. And then finally, it's something that allows the moving a boundary approach to be possible for this first iteration of it. Another benefit is that there is a host of physical processes in the wide world that are Laplacian controlled moving boundary models. So here is a viscous fingering model where if you have a reservoir of oil that's very narrow, but wide, and you blow air into it, it will produce an unstable interface with lots of bifurcations that produce a system like this. The only difference between a delta, a bifurcating delta, I won't say the only difference. One of the key differences between a delta and a system like this is that the movement of this interface is linearly related to the pressure gradient at that interface. That's how these systems work. And that is not how delta systems work, because if you have a deep channel here, and you are moving into a shallow domain, you can think of this cross section here as something like this right here, and you're eroding the sediment here, then you have to apply the shear stress to move the sediment, and you have to move it at a rate which is nonlinear with the shear stress. So rather than just taking a linear model like we have here, we add some nonlinearities. So we have an exponent and a critical shear stress for sediment motion. And these numbers can be pulled directly from a sediment transport manual, like the sedimentation engineering Bible that many of us have known, edited by Marcelo Garcia. And you can see that the critical shear stress is here between 0.04 and for fine sand, and then moving up 0.1 for muds, or 0.2 for maybe very cohesive muds. And then we have the exponent here, which is between 1.5 and 2.5. 1.5 for more bed load transport systems, 2.5 for more total load sediment transport. And the model goes as follows. This involved a lot of clever and elegant mathematics by postdoc at the time, Untao Ke. But basically, we were able to model the evolution of this boundary using the boundary element method with solving flow out here in this domain with the Laplace equation. So here's a video. And to orient you, we've got scales here that were trained to the Wax Lake Delta. So this is 10 kilometers for scale. We have a color map, which is the water surface elevation, which is here in meters. And then these light blue lines are flow lines and through the system. So as you can see, this channel prograde into the system, you can see lots of bifurcations growing, and you can see how it reflects the the flow field becomes coupled to this growing network. These light blue lines have about the same amount of discharge between each pair. So they're like equal flow lines, like you would see in a groundwater modeling exercise. But what you can see is that even though you can see that these flow lines are focused around the channel tips, that's where most of the water is coming out, but they're coupled all the way through such that there is a non-trivial amount of water entering the, leaving the channels laterally and leaving the system there. So this system bifurcates and grows over time. It has lots of bifurcations at the upstream end. We call that polyfurcation if you want. And the system continues to grow. So this is the moving boundary model. I call it MBDCN. I wanted to call it Duan Duan because that is the name of Wen Tao's cat, but he didn't want that. So MBDCN, moving boundary of a distributary channel network. So that's there. And then we can play with the controls. There are these are over here on the right are a list of the controls. First off, the shape of the basin controls how the system grows. It can never break the boundaries. So this hems in the system. The water discharge affects how rapidly the system will prograde. What I'm showing here in this diagram is the influence of these sediment transport nonlinearities. So as you go down rows, you are increasing your critical shear stress. And as you go left to right, you are increasing your exponent from 1, so a linear growth system, to 1.5. So this is the bed material transport rule, up to 2.5, which would be a total load transport rule. And for reasonable cases, again, these numbers here are built from, taken from the literature. They're not, you can produce bifurcating deltas with the right progradation rate, roughly, and the right number of bifurcations, and similar behavior along these lines. So a little more intuition for you as we go through the system. Why do these systems branch? Why do they bifurcate? This interface, this moving boundary interface, is known throughout physics. A coupled Laplacian boundary is known to be unstable at all scales. And for this reason, we add a smoothing length to this system so that we don't get channels that are arbitrarily narrow. A system, the scale of wax lake delta, has depths associated with it of 3 meters and channel widths associated with it. So we have, in this iteration of the model, we've been smoothing at roughly 100 meters. So we get channels of 100 meters. The physicists here tell me that is a quick fix to the system. There's actually a lot of nuance to that, and we're working on that. But there's a smoothing there. But larger than this smoothing length, we get branching all the time, and we get program. And the rate at which these instability grows depends on how fast water is leaving the system. So here we don't have a lot of water movement. off out of the system, increasing to at the channel tip we have the most. If we add a nonlinearity to the system, this is going to promote the fastest growing areas and inhibit the less fast growing areas. And then if you add a critical shear stress, you can turn growth off completely below the critical shear stress, which would limit channel volume. Another interesting aspect of this model, this growth, is it has nowhere in the formulation is sediment discharge to the system. So this is a counterintuitive thing. The rate at which your channel tips are growing in your system is not related to the rate at which sediment is entering the system. It is related to the rate that water is entering the system, but not sediment. So that's pretty remarkable, but it is it's something that we have, we're starting to see more and more. So in a different study that my group did here, we tracked the actual growth of distributary channel tips on the Wax Lake Delta from the 1970s when this system really got going up till 2016 or something. And it's hard to do this because these channel tips are underwater, so you have to come up with some remote sensing tricks to find them. But we did, and we tracked these things. And they all appeared to grow linearly with time. They didn't speed up or slow down, even as the area that they grew to grew larger and larger. Here's a graph of so in purple here, we have the area of the entire subaqueous delta growing. And it's hard to see any, so here is the subaqueous delta, and then below here are two independent estimates of the amount of land, the amount of subaerial land in the system. Oliver and Edmonds and Allen et al. And both of these show around 1995, the amount of new land growing over time in this system was starting to level off. And that is a function of how much sediment is getting into the system, how efficiently it's being trapped. There's lots of interesting things going on there. But the channel tips don't seem to care. They are erosional features, so they are going to propagate downstream as fast as they can erode. And while this delta front is a grading to meet up with that, it's a somewhat independent process. So that's a cool and counterintuitive thing that this model shows, and we're seeing in the field system. So here we are wrapping up this model. So distributary networks with reasonable emergent features arise from moving boundary formulations of the channels and simple hydrodynamics. So this is what we published on in 2019. And then that's right when Tae-Woo showed up, and we wanted, and it was also right around the time when Elizabeth Chamberlain published her dissertation research on Bayou-Lafourche. So here we were moving from Wax Lake Delta here, which is a 40-year-old system, to Bayou-Lafourche, which is it's a big dog in comparison. So she had a fantastic data set of cores and OSL dates revealing the progradation of this system, which are just a fantastic data set that we wanted to see how it works. So the second part of this talk is, can MBDCN model Bayou-Lafourche? And the answer is, with strengths and weaknesses, we must never forget that all models are wrong, but some are useful. This aphorism attributed to George Box. So I'm going to show you some things that I was pretty impressed with how well the model worked on, and then there's some parts that didn't. But this is the exciting thing of seeing if these models can work on long time scale, big spatial scale challenges. So a little bit about the Bayou-Lafourche system. We have it initiated around 1,600 years ago after an avulsion. Around here, it has this polyfurcation of many different channels extending from this zone here. And they extend generally to the southeast and then south in this region. We have this snarl of channels, which makes the lovely and interesting Houma, Louisiana, which is the result of the Bayou-Lafourche system growing and interacting with the relict Bayou-Teche system from a previous avulsion. And this, on the right here, I've got a digital elevation model going from 1 meter below sea level to 3 meters above sea level, which picks out this beautiful system which has just a wonderful system of major channels, minor channels, what appear to be bifurcations. I know upstream there are a lot of crevasse splay deposits that happen after the fact. But this is a complicated thing, and can we model it? While the Bayou-Lafourche system is a tremendously well-constrained system for large time scale, source to sink scale modeling, there's a lot of open questions with it too. So one of the principal ones, and very important for Louisiana, is that there are a lot of subsurface faults here, and there has been a lot of subsidence in this region, and there's been a lot of fluid withdrawal in this region, and the jagged trace, some may say jagged trace, Bayou-Lafourche, has been interpreted to have been the result of faults, that when it goes over a fault is activated, it changes the direction of the flow, the channel, and so that's a signature. So this is one interpretation that's out there. And then finally, like I showed you on the previous slide, we have this interaction with Bayou-Teche, which was a previous channel of the system that built a system that looks interpreted to look like this and comes in here. And how does the Bayou-Lafourche system work with it? All right, so we take the same system, but we start playing with the boundaries. And while we have one of the issues with going to modeling these complex systems is you started with, maybe 6 or 8 degrees of freedom, and you took a deep breath and did what you could. Now you have a lot more degrees of freedom. And so in an effort to model this system, we're going to consider sort of hypothesis testing. So rather than trying to model it spot on and recreate it perfectly, we're going to stay wrong and just see how these parameters wiggle the result. So we need a bigger channel and a larger smoothing length for a system which was clearly larger at its height in the Wax Lake Delta. We can pull sediment from the system itself. We can use friction coefficients, which seem reasonable. And we can vary a few things. We can vary these sediment transport parameters. We can vary the channel boundaries. So if we initiate the system up here, if we move the location of this western boundary or this eastern boundary, we can ask ourselves how that affects the system. And that's important because these boundaries are not something that you can draw in the rock record. They're just the place where water from the Bayou-Lafourche didn't go further. So this is just a no-flow boundary in the system. We're just going to play with what the shape of this system looks like. And then we can look at the water discharge coming in. Now, the system over the last 2,000 years of the Mississippi has not changed its mean water discharge significantly. There's been some more recent work by Wyman et al. That show that it might have been 2 to 4% smaller, but we're pretty close. But what is unknown is at the initiation of this system, how much was it sharing with the previous avulsion, namely the St. Bernard lobe, and how did that progression occur? So first we can play with the nonlinearity like we did previously with the Wax Lake Delta. We can see that it's a pretty sensitive control on how bifurcating the system is. And remember, alpha equals 1 is not really realistic. Alpha equals 2.5 also showed poor results in the Wax Lake case. So we're going to use alpha equals 1.5 again, because it has that bed material load erosion justification, even though alpha of 2.0 is not terrible from test results. So let's play around here. The first thing we did was we modified the eastern boundary. So we kept everything constant, but we moved this boundary from what our best guess of what it was. We moved it further east, encroaching into the alluvial ridge of the St. Bernard lobe, which was taking up space there. The white network is what was modeled, and the light blue line here is the location of the primary channel of the real Bayou-Lafourche. And then the yellow stars are OSL locations, which we can talk about later. But here, so we moved this eastern boundary here, and the location of the channel just bent around the western boundary each time. It likes to take the shortest route to the coast, apparently, and so the outer curve didn't affect its location that much. Even so, you can see that we had this nice polyfurcation in the upstream end, and we have a couple of channels growing before we bend to the south. How does changing the western boundary matter here? So here we kept the eastern boundary constant. We tried to, and we moved the western boundary further and further east, encroaching on the system. And here is the distance in tens of thousands of meters between the major channel of Bayou-Lafourche and the modeled channel. And as we move closer to this location, we stayed within about 5 kilometers of the system, of the real system. So first result here is the inner bend on where the boundary is significantly affects where the channel grows and moves into the system. So we should be thinking about that when we are imagining what Bayou Teche and the old Bayou Teche looked like when Bayou Lafourche was grown. So the western boundary is pretty sensitive. I started, so what do progradation rates look like? So the second really cool test here is that these red dots and their uncertainty are the OSL ages of the main channel as it grew. And here are the various progradation rates of our model. And on the left side, you can see that we prograde over 1,000 years, roughly the right amount, although we are focusing most of our progradation quite rapidly in the beginning and slowing down exponentially in the late time. But we could influence this and say, rather than turning on a full surfeit of Mississippi discharge immediately, we can start with 10% of the Mississippi discharge and control the time scale at which this ramps up. And that's what we do over here, where we let it grow over 1,000 years for this line here. And we let it grow for 200 to 400 years at this time here. And you can see that this tracks the first 5 of these OSL locations quite well. That is 1, 2, 3, 4, 5. We can hit these locations at the right time, give or take 10 kilometers or 100 years. Now, what we can't hit for any reasonable thing is this last OSL date, which is out here. That's let's not forget that. Because I haven't pointed, yeah. So when Liz published this work, I think very reasonably she looked at these OSL and said, well, we got a linear growth rate here, and while we can't hit this final point, we can get a decreasing growth rate, but that hits the first 5 ages. So we're wrapping up here. Let's ask what we've learned about Bayou Lafourche. So one of the things is what controls the changes in channel direction? Is this necessarily a signature of faults? And the answer, I think that we can show is no. In a prograding channel network, when we have bifurcations, we can change the path of the resulting channel abruptly. And is there a signature for that in the real system? Well, we can't necessarily put a bifurcation exactly here, although we can do one slightly upstream. But we can see this is perhaps the change of course from a bifurcation. Also possibly here. Also possibly here. So while we can't disprove the influence of faults with this model, there's no faults that would be included here. We can show that it can occur without the use of faults. Now, we can also ask about what the situation here was with this Bayou Teche interaction, which is a hard thing to do. And we can't specifically model a channel eating into a alluvial ridge, reactivating old channels. That's not what this model was designed for. But at the same time, we can see that maybe there was a hydraulic barrier for the main growth of the system here, but that the propensity of these channels to find direct south paths makes it reasonable that old channels could be reactivated in biotest, or that a breakthrough in a brand new channel could be occur in biotest. What have we learned about this progradation? I was pretty shocked when, without any tuning, we could get progradation rates like this, and that they improved with a reasonable amount of time, a couple of centuries of both channels of the avulsion receiving significant flow. But let's not kid ourselves. There's something weird happening with this OSL, which is either the model is breaking down, or that there is a change in the system that we haven't considered yet. And one of the things that we've proposed, but not modeled, is that late in the life of BioLaFouche, a new avulsion occurred, activating the main Bailey's delta, which is the bird's foot that you can, which is off frame here. And if that shifted the barrier late in the system and made the no flow boundary go from here to something more vertical, there's a possibility that that could be reactivated. This is an I'd love to hear your interpretations on this. It's something that we're scratching our heads about. But moving on to conclusions and wrapping up for you here. First off, we've got these, if we're going to sell out on trying to focus about how particular distributary channels prograde, and we can build a moving boundary model, which can maybe at the expense of other parts of the system, get what I think is distributary channel growth right in one of these rapidly prograding intra-avulsion systems. And we can, and then by applying to these systems in a careful sort of hypothesis testing way, we can learn something new about millennial scale delta growth. And then I'll just leave it with let's advance by trying to model specific systems over long time scales. I know that, well, Liz has published all this work. She'd be happy to share this data set, and this BioLaFouche system is just sitting here as the most beautiful target in the world for morphodynamic modelers, sitting there as a challenge to anybody to see if we can model, giving the knowledge about that system. So thank you very much for your time, and I'd be happy to take any questions.
Perfect. Thank you. Thank you so much, John. This is fascinating. Are there any questions? Please unmute yourself or raise your hand. Tom?
Thanks, Yap. Hey, John, I really enjoyed that. Very, very well thought out and logical progression of things. I don't know nearly as much as you do about this, but I'll be sort of selfish in my question and asking, as these systems evolve over time. When I think of Lax Lake Delta, I think of system that sort of came into existence with storms, so to speak, and the movement of sand. So I'm wondering, as these systems mature, what is the role of, how does the role of storms and organic carbon in the sediments affect shear stress and the overall evolution and accommodation space as these things crawl and move? I mean, when you say that water really drives this system that has a lot of sand in it, does that change as you start incorporating more organic carbon and mud into the system over time? This may be something that's just basic geomorphology that I'm ignorant of.
Fantastic question. So I'll try to answer from the perspective of the model, maybe, and we can see if that makes sense or not. The model is focused particularly on how it can get the sediments out of the way of the front of an advancing channel. There's a fire hose of water getting pushed at that mouth bar, and it's eroding it. So how does cohesion and organic carbon change that? I think that there could be a secular increase in cohesion over time that you could parameterize into the system, which might cut down on the number of bifurcations as you get further out. So that's one thing. The second thing is storms, sand, mud, organic carbon. While they don't matter in how fast the channel is prograding, they matter incredibly about the accumulation in between channels. We have these islands and the rates that they're accumulating, and the interdistributary bays and the rate they're accumulating. And these are what's going to form the lion's share of the deposit, of the stratigraphy, of the land. So the rates at which those things happen are happening at the same time, but they're independent in some ways of how the channels are making their way through the deposit.
Oh, okay. I see. Yeah, thanks very much. Hey, take care of yourself over there and try to enjoy your stay as best can.
Thank you.
I see two hands that I think Kevin was a little bit quicker. So Kevin, please go ahead first. You're muted still, Kevin. Kevin? You're muted still. Yes.
Oh, sorry. Thank you. I was muted. So this is Kevin Xu from LSU. John, this is excellent work.
Thank you.
It's a truly exciting model. So I have a question regarding the model for the Lafourche system. In your diagram, you show the water depths in the river channel as well as the delta bed. So basically the water depth is a key parameter in your model. So when you initialize your Bayou-Lafourche model, how did you initialize the paleotopography or bathymetry in the Lafourche basin? Because I don't think anyone has such data. And apparently the slope of the paleotopography will play a key role in the evolution of the morphological model. So I don't know if you initialize as a flat bed or if you use some older values from the modern topography.
Yes. So we have two different, thank you for the compliment from such a famous modeler as yourself, or inspirational modeler as yourself. So it means a lot to me. Now we have two depths. We have the channel depth, which is bulldozing into the sediments, and then we have the unchannelized flow depth. The channel depth we can get from Liz's cores, which show that the channel, the channel sands of this system were 7 meters deep eventually. So as this system moved out, they were moved into the system, it was eroding down to about 7 meters. Now, and this scales how fast the system moves relative to the shear stress. So that's the first answer. How is this flow modeled? Now, this she took from delta, the thickness of delta front sediments, and that she found that the system was building into, the thickness of delta front plus mouthbar sediments was roughly about 2 to 3 meters in Bayou Lafourche, just from cores. So these were our justifications. I think that it's fair to ask for some more sensitivity on these things because they're not pinned with the most precision. But these were our justifications. Does that make sense?
Good. Yeah. So basically, you use fixed values for the entire. Yes. Okay. So in other words, you do not consider the gradient of the paleontopography.
No. So I think it's fair to consider paleotopography so that in the upstream part of the basin, it was shallower and then it definitely gradually grew deeper. But the way this system works is it assumes that the sediment in front of the channel has built a mouth bar and has built up a deposit that can be eroded through. So, you know, muds and sands are being thrown out in front of these channels as they're pulling out, and the eroding. So you're not always encountering the full estuarine depth at the mouth here. So I think you can get away without having a high resolution bathymetric map to start out with, which is something that we don't have. I totally agree with you.
Okay. Thank you, John.
Thank you very much for your question.
Shelby, I see you raised your hand as well.
Hi, John. Thank you. I'm
Hi.
Shelby. I'm actually currently a Fulbright researcher in the Netherlands studying rivers. I was curious what you mentioned. Yeah, nice. I was curious what you mentioned, that eastern boundary maybe being responsible in reality, that shift like causing the acceleration of the propagation rates, and whether you guys ever considered having that shift within a model simulation. Would you expect like an initial reacceleration of those channels if the boundary abruptly moved like mid model?
Mm-hmm. Well, so the answer is yes. Now that is not very satisfying to be presented to you here. I think, you know, we've got a nice basis of models here, but it also has exponentially more questions of like more levers that we can tweak. So we're considering whether to do that, but we still could. Now, why? The reason it would be is, you know, water is flowing from this, you know, all along this boundary, although mostly focused at channel tips, to this boundary here. And the feeling is that if we constrained this, then we would be forcing the same amount of water through a narrower region. And thereby we could increase progradation. It is hypothetical at best. I don't have anything to preliminary to show you why. But it's a problem that we're thinking about. So does that answer your question, or do you have other ideas? Was there it doesn't seem like there was a big acceleration and discharge or something like that. Maybe the channels you could speed up if the channels got narrower. I don't see why that would happen, but that's where we're at.
No, that's cool. Your reasoning with like the narrowing of where the flow could go sounded compelling, but very cool modeling. Thank you.
Thank you. Thanks very much.
Thank you so much. For the sake of time, it's now past 3 here, and I think past 10 Eastern time. So thank you again very much, John. I have hundreds of questions as well, but I'll postpone them until you make your way over here in a few months. And if anyone else, I'm sure you can reach John via email or otherwise. Again, thank you so much, and hope to see you all next week. Bye-bye.
Thank you all for coming. Great questions. See you guys around. See you all around.